Swayam Prabha. Digital India. Educated India.
Welcome to my second lecture on advanced transfer chemistry. In my previous lecture I was discussing about the history of periodic table. Let me continue from where I had stopped. Let me tell you little bit about William Ramsay, who discovered all noble gases and published the results in 1894. So, after a periodic table was published by Mendeleev, discovering a new element has been the high point of several distinguished scientific careers, but William Ramsay, who lived from 1852 to 1916, gained a unique position in this distinguished company by adding an entire group to the periodic table. That means the group 18 elements, all inert gases, were discovered because of very painstaking systematic work carried out by William Ramsay. Although his work on the atmospheric gases earned him Britain's first chemistry Nobel Prize, Ramsay's later speculations were dismissed by many of his contemporaries. Nevertheless, during the century, since his death, some of those ideas have been partially vindicated. So, these began in 1894 following a communication from Lord Rayleigh, Professor of Physics at Cambridge University's Cavendish Laboratory from 1879 to 1884. He became an independent researcher with a private laboratory and an appointment at Royal Institution. So, having discovered that atmospheric nitrogen was denser by about very minute 0.5% than nitrogen from chemical compounds. So, that means when you separate nitrogen from atmosphere and look into its density, and when you generate nitrogen in a laboratory, the nitrogen that was generated in the laboratory was less denser by 0.5%. So, he suspected the presence of a hitherto unknown gas. That means the atmospheric nitrogen, so called isolated, taking away air, has some other component was identified during that time. So, later he learned that Henry Cavendish, after whom the Cambridge laboratory was named, had achieved a similar result many years before. We have to appreciate their analytical skills about identifying even very minute difference in the density. Cavendish had noticed that when the known atmospheric gases were chemically removed from a sample of air, a tiny bubble remained. He could not identify it, and for a century it was forgotten. So, that means he made that beautiful observation almost 100 years before Ramsay started looking into it. So, Rayleigh and Ramsay agreed to pursue this gas together, and Ramsay isolated it by passing atmospheric nitrogen over red hot magnesium to form magnesium nitrate. First, oxygen was separated from atmospheric air, and then the atmospheric nitrogen was passed over red hot magnesium. So, magnesium forms magnesium nitrate, and after completion of the formation of magnesium nitrate, he found the gaseous residue, an astonishingly indifferent body. Even fluorine would not combine with it. So, that means a fraction of very small or minute quantity of gas that was left after completely consuming nitrogen, by treating that with red hot magnesium to form magnesium nitrate, was found to be inert compared to fluorine, why he say fluorine is the most reactive element and it can combine with literally any element that is present in the periodic table. That is the reason he says it is an astonishingly indifferent body and even fluorine would not combine with it. He is noted, Henry Cavendish is noted for his discovery of hydrogen called inflammable air, described its density, showed it forming water on combustion in a 1766 paper. So, Anthony Lavoisier later reproduced Cavendish experiments and gave the element its name. In British Association meeting, both Rayleigh and Ramsay announced the discovery of new element to the Royal Society in January 1895. They named it argon, derived from the Greek word for idol. Although spectroscopic analysis by William Crookes confirmed that the new gas had a distinctive line pattern, some critics disputed its elementary status. Ramsay ignored them and was soon pursuing another mystery gas. So, once after the discovery of argon, he did not give up, he continued working to find out other missing gases. So, chemists know your place refer to inert gases. This is some sort of statement made that time. So, in February 1895, the British mineralogist Henry Myers alerted Ramsay to an important unusual property of cleveite, a mineral consisting mainly of uranium oxide. So, William Hellbrand, a chemist with the United States Geology Survey, had noticed that heating cleveite with sulfuric acid generated an unreactive gas which he presumed was nitrogen. On learning this, Ramsay carefully finished the experiments he was working on, obtained a sample of cleveite from a London mineral dealer for 3 shillings and 6 pence, that means 14.5 pounds now, and soon he had a sample of Hillbrand's gas. This is called Hillbrand's gas. Okay. 2 days of chemical analysis eliminated all known gases except argon from consideration, but the new gas spectrum was not argons. So, that means whatever the gas he obtained, he eliminated all other gases except argon for consideration, and the new gas he found showed a different spectrum from argon. So, within a week Crookes confirmed that it was helium, an element identified spectroscopically in the Sun in 1868, but previously undetected on Earth. His discovery of terrestrial helium was announced to London's Chemical Society in March 1895. So, Ramsay's discovery of terrestrial helium was announced to London's Chemical Society in March 1895. By then, Ramsay believed that further inert gases occupying a new group in the periodic table were awaiting discovery. So, James Devar, another contemporary of Ramsay, opposed Ramsay's concept of a class of inert gases. His ideas were loudly opposed by Devar, a professor of chemistry at London's Royal Institution. So, anonymous attacks on Ramsay's work also appeared in chemical news, probably written by Devar's friend Henry Armstrong. So, Rayleigh soon abandoned this chemist's quarrel and returned to the more gentlemanly world of physics, where, as he later commented, second rate men seems to know their place. Ramsay however battled on. That means Rayleigh, after seeing unworthy criticism, he gave up and he got back to physics research, but however Ramsay continued. One obstacle to argon's acceptance as an element was its apparent atomic weight. Its vapor density relative to that of hydrogen I am talking about was 19.9, which indicated a molecular weight of 39.8. So, that means probably it is very similar to a diatomic species, but the ratio of its two specific heats at constant pressure and at constant volume implied that the gas was monoatomic. So, this gave argon an atomic weight higher than its neighboring potassium, that is potassium atomic weight is to be precise 39.0983, and hence a somewhat incongruous position in the periodic table. Two other pairs of adjacent elements, tellurium and iodine and cobalt and nickel, were similarly misplaced in the table. So, many chemists believed that their published atomic weights were erroneous, but Ramsay's critics rejected this explanation for the argon potassium anomaly. Instead, they argued that the new gas was an allotrope of nitrogen with the formula N3. 2 decades later, Frederick Soddy's introduction of the concept of an isotope would explain the enormous atomic weights, and Henry Moseley's determination of atomic numbers would rationalize the periodic table, but meanwhile the onus remained on Ramsay to justify his claims. To confirm the status of argon and helium and to isolate any further atmospheric gases, Ramsay needed large scale facilities for liquefying and fractionally distillating air, but Britain's leading expert on this field was his opponent Devar, inventor of vacuum jacketed containers, still known as the Devar flask. Whatever we are using today are all invented by Devar, vacuum flasks. So, instead Ramsay turned to William Hampson, with whom Devar also has dispute, to get that facility of liquefying in larger quantity and distilling air. Hampson was an Oxford Classics graduate who trained as a barrister before emerging as a scientist. In 1895 he patented an innovative process for liquefying gases and licensed it to Brin's Oxygen Company, later to become the industrial giant British Oxygen. So, now it is called BOC. So, Hampson provided advice and some liquid air, but Ramsay and his assistant Maurice Travers built their own distillation apparatus, much of it improvised from recycled equipment. The challenge facing Ramsay and Travers was greater than they realized. Although argon is relatively abundant, forming almost 1% of atmospheric air, the other noble gases are present in very tiny amounts. Neon about 20 parts per million, krypton 1 parts per million and xenon 0.1 ppm. So, nevertheless by mid 1898 they had isolated enough of these gases to map their spectra and confirm their chemical inactivity and also their chemical identity. Unfortunately, Ramsay also briefly claimed the discovery of another element, meta-argon, with an atomic weight slightly less than argon's and different lines in its spectrum. So, others could not confirm this result, and Ramsay soon found that anomalies were due to traces of carbon monoxide in his argon sample. So, announcing this, he commented ironically, "Should we under such circumstances regret the publication of an error? It seems to me that an occasional error should be excusable." So, when you are working with great deal identifying new elements, I think such small errors can be neglected. So, no one can be infallible, and besides in these conjectures one has always a large number of good friends who promptly correct the inaccuracy. So, this is where healthy criticism and critical evaluation of research plays a major role. So, during this period Ernest Rutherford and Pierre and Marie Curie had found that some radioactive elements released a heavy gas which Rutherford called emanation. Since it appeared to belong to the noble gas family, it naturally attracted Ramsay's attention. So, this radioactive gas took different forms, thorium emanation and actinium emanation, which were eventually identified as isotopes of the same element. Radium emanation, later simply called radon, was the longest lived with a half life of 3.8 days. In 1903 Ramsay joined with Rutherford's former collaborator Frederick Soddy to study it. By the time what happens, Ramsay's co-worker Travers has to leave to India to become director of Indian Institute of Science. That means Ramsay and Rutherford found that a sealed container of radon, if left standing for a time, eventually generated the characteristic spectrum lines of helium. So, this important result supported Rutherford's suggestion that the positively charged alpha particles emitted by radon were actually the nuclei of helium atoms 2He4. But after Soddy moved on to Glasgow University in 1904, Ramsay's later work on radioactivity proved less fruitful. So, Ramsay hoped that bombarding other elements with radon's alpha particles might change their chemical identity. His eagerness led him to announce some spurious discoveries. For example, in 1907 he claimed that electrolyzing a copper salt dissolved in water previously exposed to radon converted the copper into lithium. Other experiments could not replicate these results, and physicists including Rutherford dismissed these results as impossible on theoretical grounds. Sometimes too much of speculation is also not good when we have some good results. However, Ramsay's later work was unsuccessful. In 1910, assisted by Robert Whitelaw Gray, he measured the density of radon precisely enough to establish that its atomic weight different from that of its parent element radium by the weight of one helium atom. So, given the tiny size of his sample and radon's short half life, this was a remarkable achievement. It also supported Rutherford's conviction that alpha particles were helium nuclei. When we talk about the periodic table and the properties that depicts today in understanding chemistry, it is very appropriate to talk about Henry Moseley. So, Henry Moseley determined the atomic number of each of the elements. He modified the periodic law to read the properties of the elements vary periodically with their atomic numbers. That means physical and chemical properties of elements are the periodic functions of their atomic numbers was what the information provided from extensive work carried out by Henry Moseley. In 1914 he predicted that there were 3 unknown elements between aluminum and gold, and he concluded that there were only 92 elements up to and including uranium. So, Henry Moseley lived between 1887 to 1915, that means he lived only for 28 years. In 1913 through his work with X-rays he determined the actual nuclear charge of the elements. He then arranged the elements in order of increasing atomic number, that is nuclear charge. When we talk about Henry Moseley, he mentioned that there is in the atom a fundamental quantity which increases by regular steps as we pass from each element to the next. This quantity can only be the charge on the central positive nucleus. So, Moseley's research was halted when the British government sent him to serve as a foot soldier in World War I. So, he was killed in the fighting at the age of 28. So, because of this loss, the British government later restricted its scientists to non-combatant duties during world wars. Now, let us look into important chemist and a physicist who has contributed significantly to the understanding of radioactivity, Marie Curie. So, Marie Curie was born in Warsaw, Poland in 1867, and her father was a physics teacher. So, in 1891 she went to study at the Sorbonne in Paris. She received a degree in physical sciences in 1893 with highest honors and in mathematics in 1894. Same year she met Pierre Curie, a noted French physicist and chemist who had done important work in magnetism. So, Marie and Pierre married in 1895. This scientific partnership achieved so much and contributed remarkably to science. On April 20th, 1902, Marie and Pierre Curie successfully isolated radioactive radium salts from the mineral pitchblende in their laboratory in Paris. In 1898 the Curies discovered the existence of the elements radium and polonium in their research of pitch blende. 1 year after isolating radium, they shared the 1903 Nobel Prize in Physics with French scientist A. Henry Becquerel for their groundbreaking discovery of radioactivity. She is the first woman recipient of Nobel Prize. Pierre Curie was appointed to the chair of physics at Sorbonne in 1904, and Mary continued her efforts to isolate pure non-chloride radium. So, on April 19, 1906, Pierre Curie was killed in an accident in the Paris streets. So, although devastated, Marie Curie vowed to continue her work, and in May 1906 she was appointed to her husband's seat at the Sorbonne, thus becoming the university's first female professor. In 1910 with Devar, she finally succeeded in isolating pure metallic radium. For this achievement, she was the sole recipient of the 1911 Nobel Prize in Chemistry, making her the first person to win a second Nobel Prize. So, this is Curie at the young age, and this is with Pierre Curie on their way to work. So, Curie's daughter Irene Curie was also a physical chemist, and with her husband Frederick Joliot was awarded Nobel Prize in Chemistry in 1935 for the discovery of artificial radioactivity. So, Marie Curie died in 1934 from leukemia, blood cancer caused by 4 decades of her exposure to radioactive substances. In 1962 another Nobel Prize was received by Mary's second daughter's husband, who was the director of UNICEF. That means this Curie family has a credit of 5 Nobel Prizes, something remarkable and unbelievable achievement. It is appropriate to remember Glenn T C Burke when it comes to post-uranium elements or man-made elements. After co-discovering 10 new elements were synthesized in the laboratory, all man-made, he moved 14 elements out of the main body of the periodic table to their current location below the lanthanide series. These became known as the actinide series. Of course, that I have shown here from 91 thorium to lawrencium 103. He is the first person to have an element named after him while still alive, Glenn T C Burke. When that element was named after him, what he obeyed I have shown here. I quote, "This is the greatest honor ever bestowed upon me, even better I think than winning the Nobel Prize." I unquote. So, on 23rd March 2016 in a conference call, a group of researchers decided the names of 3 of the latest elements in the periodic table. First, tennessine was proposed for atomic number 117, then moscovium for atomic number 115. Only the heaviest element yet discovered was the element 118. It remained nameless, and then in the conference one scientist Yuri Gagarin was there. Somebody said, "Gagarin, please leave the conference." So, the remaining collaborators then made a unanimous decision to name the atomic number 118 element after Yuri Gagarin. So, that means Yuri Gagarin became the only second living person after US chemist Glenn C. Burke to have an element named in their honor, Gagarin. That means the modern periodic table completed with the naming of the last element 118 after Gagarin. And the reason is very simple and very appropriate for naming atomic number 118 as Gagarin, because Gagarin had not just led the international team to their discoveries, he had pioneered the very techniques they used. In 1970s he had invented cold fusion, not the hypothesized low energy nuclear reaction, but a technique to produce super heavy elements crucial to the discoveries of elements 104 to 113. Now his expertise in a new technique branded hot fusion had stretched the boundaries of knowledge to the end of the 7th row of periodic table. So as Sherry Enyl, director of Texas A&M's Cyclotron Institute says, I quote, "He has been a luminary in the field since forever. He is the grandfather of super heavy elements," I unquote. So this is scientist Yuri Oganesson, the last known element in the periodic table being called as Oganesson. So let us look into the modern periodic table. So modern periodic table ends with Oganesson in the column of noble gases here. After radon, Oganesson is there. According to the theoretical predictions, Oganesson will readily give or can take electrons and it forms, its atoms may clump together. Few atoms of Oganesson made by chemists survived for less than a millisecond. That means you know how difficult it is to work with to establish their properties. Smashing atoms together is being continued in search of elements beyond 118. So let me stop at this juncture and continue more interesting stories about periodic table in my third lecture. Until then, have an excellent time. Thank you.